Have you ever really looked at a glucose test strip and wondered what's happening inside? It's pretty amazing. It's basically a miniature laboratory that turns a simple chemical reaction into an electrical signal, and it does it all in a matter of seconds. In this explainer, we're going to break down exactly how that magic works, from that single drop of blood all the way to the final number you see on the screen. You know, for millions of people, these little devices are an absolute lifeline. They're super fast, an easy way to measure glucose, blood sugar. It's totally essential for managing diabetes, and the whole entire process kicks off with just one tiny drop of blood. But what happens after that drop hits the strip? Well, that's where the science gets really, really cool. So if you're the one using it, the whole system seems pretty straightforward, right? You've got three main parts. There's the lancet. That's just the tiny needle for getting the blood sample. Then you have the meter, which is the brains of the operation that shows you the reading. And then there's the star of our show today, the test strip. This little disposable strip is where all the complicated, fascinating chemistry happens. All right, so here's our roadmap for today. We're going to start with the absolute basics. Then we'll take a little trip back in time to look at the very first glucose sensors and a pretty major flaw they had. After that, we'll see how the second generation completely solved that problem, and we'll do a deep dive into the chemistry that actually creates an electric current. And finally, we'll uncover how the meter turns that current into the final reading. It's going to be a fun one. Okay, so at its core, a glucose monitor is something called an electrochemical biosensor. Yeah, I know, that's a mouthful. But all it really means is that this device has one single mission: to measure the glucose in your blood and to do it fast and accurately. And the way it pulls that off is by converting that glucose into a signal it can actually read, in this case, an electrical current. So let's get into the engineering story here. The very first glucose sensors were, a brilliant idea, but they had a huge fundamental flaw. They were built around a chemical reaction that needed not just the glucose from your blood, but also the oxygen that was floating around in there too. This diagram here shows us exactly how those early sensors worked. So follow along with me. The glucose from your blood would react with an enzyme they put on the strip called glucose oxidase, or just GOD for short. Now, for this reaction to work, it needed something called an electron acceptor, and in this version 1.0 model, that acceptor was oxygen. This whole process created hydrogen peroxide, which was then measured by an electrode, and that measurement generated a current. So the thinking was, more glucose means more hydrogen peroxide, which means a stronger current. Sounds simple enough, right? But there was a catch. And here is the problem, laid out perfectly. What this quote is saying is that there's about 10 times less oxygen in our blood than glucose, especially if your blood sugar happens to be high. This created a massive bottleneck. The reaction would basically run out of oxygen long before it had finished measuring all the glucose. And the result? Dangerously inaccurate low readings. So, to sum it up, this first design was a real problem child for three big reasons. First, that oxygen deficit we just talked about, the #1 cause of bad readings. Second, it needed a pretty high electrical voltage at the electrode to work, which meant other stuff in the blood could accidentally react and mess up the measurement. And finally, the byproduct of the reaction, hydrogen peroxide, was actually damaging the GOD enzyme that the whole test relied on. So yeah, they definitely needed a new solution. And then came the breakthrough, the second generation of sensors. This was the absolute game changer that made the reliable home glucose monitors we have today possible. Scientists figured out a way to take oxygen completely out of the picture. Now, take a look at this diagram. This is such a clever solution. Instead of relying on the unpredictable oxygen in your blood, this new design uses something called a mediator. You can see that the glucose still reacts with that same GOD enzyme, but now this man-made mediator steps in to shuttle the electrons over to the electrode, creating the electrical current we need. So, what exactly is this redox mediator? Well, think of it like a dedicated, high-speed shuttle bus just for electrons. Oxygen was kind of like a city bus. Unreliable, you never knew how much of it would show up. But the mediator, that's a private limo. Its one and only job is to grab electrons from the glucose reaction and ferry them over to the electrode, over and over again, super efficiently. And the benefits of this new design were huge. First, and most importantly, it solved the oxygen problem for good. No more bottleneck. Second, the mediator they chose, potassium ferricyanide, is really gentle on the GOD enzyme. It doesn't damage it at all. And third, and this is a big one for manufacturing, you can print the exact right amount of mediator onto every single test strip, which guarantees a consistent, reliable test every single time. All right, so we've got our reliable mediator in place. Now let's get into the real nitty-gritty of the chemistry.
For anyone studying this, you're going to want to pay close attention to these next few slides. This is really the heart of the entire process. We're going to trace exactly how the chemistry on that strip creates a real, measurable electrical signal.
Okay, first, let's bring back our star enzyme, glucose oxidase, or GOD. The most important thing to know about GOD is that it is incredibly picky. It has what's called an active site that is perfectly shaped to grab onto glucose molecules and pretty much nothing else in your blood. This selectivity is the secret to the test's accuracy. It ensures we're only measuring glucose.
And here's the hero of the second-generation story, our mediator. In almost all modern test strips, this is a chemical called potassium ferrocyanide. This specially engineered molecule is our artificial electron acceptor, and it does the job that oxygen just couldn't do reliably.
So let's break this critical reaction down into 3 simple steps. Step 1. The blood meets the chemicals on the strip. The glucose oxidase enzyme finds a glucose molecule and chemically changes it into something called gluconic acid. Step 2. This is where our mediator, ferrocyanide, comes in. It swoops in and takes electrons from that first reaction. Now, when it accepts those electrons, it actually changes its own chemical state and becomes ferrocyanide. And here's the most important part. For every single molecule of glucose that gets converted, exactly 1 molecule of ferrocyanide gets created. It is a perfect 1-to-1 ratio. Step 3. The meter applies a tiny voltage to the strip. This basically encourages all that newly created ferrocyanide to give back the electrons it just took. That movement of electrons is the electric current, and the meter is designed to measure that flow with incredible precision. Which brings us to the final piece of the puzzle. The meter has measured an electrical current in nanoamps. But that's not a blood sugar reading, right? How does the meter translate that tiny electrical signal into the number that finally pops up on the screen?
The secret is baked right into the meter's memory. It's this graph, called a calibration curve. Every single glucose meter is programmed with this information at the factory. The line going across the bottom represents the glucose concentration, and the line going up represents the electrical current. And as you can see, it's a nearly perfect straight line. What that means is the relationship is predictable. If you double the amount of glucose, you're going to double the amount of current. It's this linear relationship that lets the meter do its final calculation.
Now, the steepness of this line, its slope, is a really important concept called sensitivity. And in this case, a high sensitivity is exactly what you want. A steep slope means that even a tiny little change in your blood glucose creates a big, easy-to-measure change in the electrical current. And that, of course, makes the final reading much, much more precise. And this right here is the magic number. For this particular sensor system, the sensitivity works out to be about 0.72 nanoamps per micromolar of glucose. So the meter's job is actually simple math. It measures the current in nanoamps. It divides that number by the sensitivity, and bam! Out comes your glucose concentration. It's just a simple calculation that turns all that complex chemistry into a useful, life-saving number. So let's just stop and appreciate this for a second. You have a complex laboratory process, enzymatic reactions, electron transfers, precise electrochemical measurements, and it's all happening in just a few seconds on a tiny, disposable piece of plastic. It's truly incredible. And it really makes you wonder, doesn't it? What other complex medical tests are we going to see miniaturized and brought right into our homes next?